The next presentation will be on dual space access architecture, combining advanced rockets and space elevators. And once again, please welcome author, professor, veteran, and president of the International Space Elevator Consortium, Dr. Pete Swan.
One of the things I'd like to do is thank the Foundation for the Future and all the people that have been involved in that, because it turns out that your objective, your mission, is really quite important to many, many people, including us. Okay, I think we're ready. What I really want to do is kind of congratulate all the previous speakers, because they came up with some really, really significant points. And that's where we're going. We have a group of dedicated professionals that are charging off in different directions. And, you know, the role of the ISEC is to just make sure that they're somewhat in parallel. So we're out there having great successes individually. But the real kicker in this whole day is most of us have said that space elevators are essential. Now, we all know what essential means now in today's world. You know, the new normal is different than the past, and essential workers is really a praise out there. What we want to say is that space elevators really, really need to be done if we want to really move into our dreams that so many people are expressing. So our mission is to move massive cargo in a green manner to GEO and beyond. And as we discussed earlier, the price of travel is not the issue, it's the economic development that would occur when we get out there. And I'm a true convert to Kevin's whole philosophy. I think there's really a lot to be said for that. So the strategic approach we need to take is, how do we go from where we are to an operational space elevator? And the way we do it is we join rockets. We encourage rockets. The advanced rocket people are doing marvelous jobs. They're providing systems that will fulfill our needs, such as low Earth orbiting constellation of satellites, and doing weather satellites, and doing all that kind of stuff that's been traditional. What we want to do is join that road to space and provide another capability, but basically to provide mass to GEO and beyond. And if you remember on previous charts, I said 22,000 tons was what we've put into Earth orbit since 1957. We want to propose a lot more than that. We want to be an aggressive teammate of rockets. I just put this in there to make sure everybody remembered where we were. But the first step is we want to have an evolutionary approach for humanity moving off planet. But the strategy is dual space access architecture. A lot of this is in our book that we put on the website. So, you know, if you check that out, you'll be in pretty good shape. In addition, we were talking earlier in Fitzer's discussion about the categorization of the technologies. Where were we? What was the success in different areas? These two books really hit that pretty hard. And they do use the traditional TRL level, technology readiness level, to try to combine it. And it was contributions from 40 space professionals from around the world, the Ukraine, Russia, China, places like that. So a permanent space access infrastructure. It's going to provide jobs, jobs, jobs. And that's really what we're after in the sense of future missions to space. And the real kicker is we're going to provide freight to GEO and beyond. Now, the strengths of Space Elevator, if you notice, I didn't really talk about that in the last talk. The strengths of Space Elevator are remarkable. And if you take out the equation about price and you just discuss it as a capability, you just shake your head and say, what a marvelous opportunity. How many people were looking at, you know, San Francisco from across the bay in the early days and saying, oh, where can I get a boat? What can I do? Or take the road all the way down south and back up. Nowadays, you just hop on a high-speed train or get in your car and you go across the Golden Gate Bridge and all of a sudden you're there. That's the idea. We want to change the approach. And, you know, the characteristics of a bridge are very, very similar to what we were proposing. So the key is we want to have a combination of rockets and space elevators. But of course, you have to recognize the shortfalls of both of them. The conundrum of rockets boils down to how much delivery mass do you provide to the destination? If you want a pizza on the moon, you'd like to order it and have it come in a timely manner, but you'd also like to have it cost less than a full set of rockets. To deliver something to the surface of the moon, it takes about 99.5% of the mass to get there. Now, we argue that the first stages are reusable nowadays, and they're a lot cheaper and everything else. That's not the point. The point is you only deliver 0.5% to your destination. Whereas if you take other infrastructure approaches, you can deliver 70, 80% to your destination. So the delivery of product to the destination is the real strength of space elevators. So we're ready to really start the development program. We've talked about that before, but our strategy of the dual space access architecture is what we're going to talk about now. And we get into some details about each of the sets of strengths and weaknesses. We all have some, both strengths and weaknesses, but the promises of space elevators are so remarkable that we really need to go forward with it. Mass to orbit. We came up with these numbers over 20 years. Turns out Brad Edwards started way back in 2001 or so and came up with the number 20 metric ton tethered climbers. And we all argued with him about how much would be tethered climber and how much would be payload and everything else. It took about 2 or 3 years before we finally came up with the answer. About 6 metric tons of climber and 14 metric tons of payload. Well, let me tell you, we had that discussion again very recently. We're having a tethered climber design study. They're talking about the interface between the tethered climber and the tethered material. And you're going to hear about that from Dennis Wright in a few minutes. But the real kicker is the terminology is still being discussed. How much mass can we really move by space elevators? In addition, the Japanese corporation, the Obayashi Corporation, published in 2014 a document that said, I can design and build a space elevator. And they had a different set of criteria, starting criteria than we did. Ours was robotic only, future, we'd have people. They started with people. We need a space elevator that moves people. So with their starting point of moving people, they came up with 100 metric ton tethered climbers. Well, if you put that in the criteria to start a design, you obviously need a safety factor for humans and radiation shielding for humans, et cetera, et cetera, et cetera. So they came up with 100 metric ton climbers instead of 20. Their payload was 79 metric tons delivered to the end. And that's what they came up with back in 2014. It turns out to achieve that, they needed 2 tethers together. So their one space elevator tether actually had 2 independent tethers running parallel. And you can basically think that as a demand for safety, reliability of 2 versus 1, like airplanes having 2 or 4 engines. So the numbers of mass to geosynchronous and beyond have traditional traditional development, and they've come up with some pretty good numbers. Now I'm just going to use this as an example. You saw this earlier with David Dodson, and it's a very, very important concept. Not the numbers and everything, although they're important also, but David did a good job of expressing the need. We need space-based solar power. But I'm going to show this as a mechanism of having a dual space access architecture. Okay, let's look at that orange line. That's what we need. That's what we need. You can look at these numbers again. All this stuff will be on the web and in the video. And so we have a need on that orange line. If we launch 1,000 times a year, now that's just a random number, but basically 1,000 times a year at 20 tons to geo, and that's what a Starship can do, 20 tons to geo, that gives you that bottom line. And if you notice, it's approaching the blue line, which is minimum need in electricity. And it doesn't get there for a long time. So what we want to do is we want to use rockets as the initial capability of putting prototype satellites in low Earth orbit so Dr. Mankins and his team can test the technologies. He can work on the efficiency of solar collectors. He can work on the transition of the energy from the solar collectors to the antennas, radiating it down. He can work on thermal characteristics of the satellite, et cetera, et cetera, et cetera. We can do that in LEO, where we can actually get to it every day and work on it and all that kind of stuff. Even have humans up there assembling the major parts. Remember, these satellites are 10,000 tons. Now, the prototypes wouldn't be 10,000 tons, so you'd be working on smaller ones. But the key is working LEO. Well, rockets are great for that. So what we want to do in the solar power satellite program is use rockets to start the program. Put the prototypes up in low Earth orbit, and then even put the primary #1 operational satellite up the geosynchronous. Whoops, 10,000 tons divided by 20. So how many is that? That's a bunch of launches, but we can use rockets to put the first one up. So then once you have the first one up, now you need to assemble a lot of them at geosynchronous. That's where we bring in space elevators. So it's a dual space access program. Rockets to get it started, space elevators to really fill out the demand and put the mass up there, the geosynchronous. Now remember what we're doing. We're going to have 350 satellites that are each 10,000 tons. So we have to put them up at geo, and then we have to use Fitzger's concept of assembly in the geosynchronous region where we're going to have tremendous business develop. We're going to have franchises. We're going to have all kinds of activities at geo, one of which is assembling space solar power satellites. So you take a whole bunch of 14 metric ton payloads and you pull them over and you put them together as Lincoln logs till you get 10,000 pounds. And then you take that solar power satellite and move it in the geo arc to where it needs to be. So it's assembly at geo, but you're only going to get that mass to geo in a timely manner if you use space elevators. So that's a dual access strategy, combining both rockets and space elevators, leveraging the strengths of both and putting it into a program that will implement your needs. Now, we've talked about reference missions, or I have earlier in my first talk, but if you're going to do solar power, 5 million tons to geo, or you're going to put 500,000 tons onto the moon, or you're going to do Mr. Musk activities for 1 million tons to Mars, you really need to have a combination. Mr. Musk has claimed, I listened to him the other day, that he's going to have his starships going to Mars in the 26 time period. What's that? 5 years? 5 years. And he's going to have people going to Mars before 2030. Before 2030. So we're not going to be there to support him at that point. So he's going to move his people and his supplies to Mars on rockets. Then he's going to move his people and everything to Mars. And then we can come in and move the heavy stuff for him. So the idea is we use the strengths of both activities. So if we look at Mars and say, how do we get there? Today, and by the way, Mr. Musk's plan is you wait 26 months, and then you have a window. And then you launch into the minimum energy transfer, which is about 3 kilometers per second departure from the low Earth orbit. That's not true. It's 3.3 kilometers per second release from the sphere of influence of the Earth, which is way up there. And then it takes 7 to 9 months to get there. But you have to wait 26 months. So what we want to do is we want to show what the strengths of space elevators adds to the equation. The new concept, if you depart from the apex anchor at 100,000 kilometers up there, you have tremendous potential and kinetic energy. You can get to Mars in 61 days. Now that's the best. Overall, you can get there in like 400 days on the worst lineups, and the average is about 140 days or something like that. So you can get there relatively fast compared to today's world. And here's the secret. You can toss it toward Mars every day. Now, some paths are a little longer than others. It might be 400 days to get there. But what you do is you put your hammer and nails in, routine stuff on the 400-day trip, and you put your pizza and beer or whatever on your 61-day trips. So the kicker is space elevators can provide massive approaches. I'm going to just visually show this. Don't worry about the words and all that kind of stuff. This is what we did in the last 9 months. 3 missions left from Earth to go to Mars. What was it? UAE, United Arab Emirates, China, and America. Took 7.5 plus months to get there. UAE was the 5th nation to arrive at Mars and go into orbit. The Chinese were the 6th nation to arrive. We arrived after those guys, and we waved at all the other hardware we had in orbit. So, that was fun. But the point is, it was significant achievement for the UAE and the Chinese. Okay, this is a little pretty picture of departure. The Earth's going 29 kilometers per second. We leave the sphere of influence, which is 1 million kilometers up there, at 2.9. So we've got to leave from the low Earth orbit 3.6. We lose a lot on the way up. Here's our little pretty picture. We're departing at 7.76 kilometers per second. If we had an optional anchor that went all the way up to 150,000, you go faster. If you go to 163,000 kilometer altitude, you can leave our solar system without a rocket. Okay, pretty picture. If you have more energy, you have a bigger ellipse. That's just to show the size of the ellipses versus a Hohmann transfer that just barely makes it to Mars. What we want to do with that high velocity, though, is not do the traditional approach with the ellipse. We want to cut the corner. So we enter these ellipses, they're called orbits. We enter the elliptical orbit on its side and take the fast transit to Mars. Now, if you miss it at that point, you could probably meet it over there on the other side. So there are all kinds of options. But the real kicker is we're doing it differently. And we have a buzz schedule. Whoa, wait a minute. I want to go to Mars. I want to send my hammer. So I go over to the Indian Ocean Space Elevator and leave on Tuesday. And it takes 400 days to get there. And then I come over here and I want to send pizza. So I go to the Pacific Space Elevator and leave on Thursday. And it gets there in 79 days. So the real kicker is it's routine. It's every day. You can release every day, 61 days, rapid and massive capability. So what we're providing is so much more than rockets can provide. This is an old chart that shows we've only done 22,000 tons. If you notice, 22,000 tons, 16 and a half is just putting the space shuttle up there. By the way, I counted the space shuttle, because it was an orbital mission. So I counted it. So that was most of the mass. So it's kind of like scary about that. But anyway, if you want to use Mr. Musk's mission, just as an idea, then to do his job, he needs 40,000 launches every 26 months. He has to launch a whole bunch of stuff. So at 40,000 launches, that's a long time. So that's a little shaky. But that's what he has planned. I propose that what we want to do is have Mr. Musk send his people and all the early hardware as soon as he can and start a colony. But then when he really gets hungry and he needs a lot of logistics, he ought to call for space elevators. Now, the real kicker is space elevators are evolutionary. It's the first big step. We kind of like stumbled off on the Apollo program and stuff like that. What we need is an infrastructure that's a big step. But elevators are also revolutionary in that it changes the equation on delivery of mass. We're no longer limited by the rocket equation. I came up with a term I like, which is liberating movement of logistic cargo by electricity. Kind of funny. But anyway, the kicker is we break the equation. Okay, that's what I have on the charts and everything. So
well, you're really good with time.
Oh, well, good. Hey, that's good. I got 2 minutes on my cutback time.
Yeah. So is there one question in any of the chats? Something from Kevin Berry.
Yeah, I can just ask it directly. Dr. Swan, can you take and elaborate further on kind of the even potentially greater opportunity of not just departing off of the tip of the space elevator, but actually gainfully using the acceleration you get falling from GEO, and sort of the discussions that have been discussed about how that can be used to accelerate objects even greater speeds and thrown further out?
Okay, it turns out there was a recent paper by Professor Matthew Peat, and it's an interesting paper. Now remember, I taught orbits for 2 years at the Air Force Academy, so I think I understand a little bit about orbits. But anyway, he teaches orbits at ASU, and we've been working with him on the research. So he decided to publish a paper that took the release of payloads from the space elevator from archaic, which is what I look at, which is you get it up to the space elevator, you stop it there, you pump it with gas or whatever, you know, put people in it, whatever, and then you release it. So your inherent velocity is 7.6 kilometers per second. Now, if you then do what he was talking about, you could release this, the payload from the space elevator at geosynchronous and keep it on a nice line by having it attached to the space elevator, but not slowing it down at the tether end. You just let it accelerate from geo all the way out to 100,000 kilometers, and you now can leave the solar system with no rocket fuel. And then he had 2 more tiers. He's calling them tiers. Mine was tier 0, you know, like mundane. That would be tier 1 to have an acceleration. And then tier 2 and 3 added a capability to depart at an angle other than the equatorial plane that you're in. If you do a normal space elevator thinking, you release and you're in the equatorial plane, and all its thinking planets are in the ecliptic plane. So you have to have rocket fuel to change from equatorial to ecliptic. And he was able to show how he could do inclination changes with mechanisms at the end of the tether. And what he says at the end of his paper is he can get to any planet in a reasonable time, releasing from the space elevator every day of the year.
Wow.
Oh yeah, it just blows your socks off.
It does. We need to move on to the next topic, if that's all right. We don't want to cut Dr. Wright short.
Oh, no.
All right. Thank you very much, Dr. Swan.